Hi everyone. So last time we finished with Bezout's identity. So let's use it to prove the following result. So the way I like to see this result is by the prime factorization theorem. And actually here, if you have that A divides BC and the GCD between A and B is 1, so then A divides C. So here, if A divides B and C, then that means that A fits into BC. So then what this tells you is that the prime factorization of A is inside of the prime factorization of BC. So BC has certain primes for its factors that is equal to those precisely of those primes of A. But since A doesn't fit into B, so then it must fit into the other element where A divides that as it divides B and C. So that's the logic. So this logic is also captured by the following result. So let's see, so we can use Bezout's identity to prove it, since A and B is equal to 1. So that means there is a linear combination U and V inside of the integers such that A times U plus B times V is equal to 1. But if we multiply by C, then you have A times C by U plus B times C times V is equal to C. And if A divides B and C, then you can replace BC by A. So we have that A multiplied by R times V is equal to C. So if you factor in an A, then you have CU plus RV is equal to C, and that means that A divides C. So just let's try to analyze it heuristically a little bit. Since the GCD between A and B is 1, so that means that you can generate all of Z by the linear combination of A and B. So in particular, you can generate C. So then, since you can reach C, then that means that since A divides BC, so then that means you can reach C by A. Yeah, so again, the logic here is that if the GCD between A and B is 1, so that we can reach all the possible integers as linear combination of A and B. So in particular, we can reach the also C as well. But since A divides one of the possible ways where we can reach that specific linear combination that reaches C, so then in particular it must fit into C. That's essentially another reason as well from the prime factors that I've mentioned. Okay, so let's see what we can, let's solve a couple of problems. So let's start with question 8. So prove that the, the GCD between n and n plus 1 is equal to 1. So let d equal to the GCD between n and n plus 1. So therefore, d divides n and divides n plus 1. So in particular, it must divide 1, right? Because we would take n plus 1 minus n, which is 1. So d must divide 1. So therefore, the GCD d is less than or equal to 1, but what we mentioned before, that d is bigger than or equal to 1, so therefore d is equal to 1. Yeah, so we use the following result. Use the following result to prove it. For b, if a divides b and a divides c, prove that a divides br plus ct for any r and t belongs to z. Okay, so if a divides b, then you can write b as a multiple of a, and if a divides c, then similarly we can write c as a multiple of a. So that means that from these guys we have that b times r is equal to a times u times r, and c times t is equal to a times v times t for ur belongs to z and vt belongs to z. So that tells us that if you add br plus ct, then that would be a multiplied by ur plus a multiplied by vt. So you can factor an a, and then you get that a divides br plus ct. So in particular, you get that if r, because here r and t can be anything, so if r is equal to 1 and t is equal to 1, and if r is equal to 1 and t is equal to -1, and if r is equal to -1 and t is equal to 1. Then we get that a divides b minus c t, or b plus ct first, b or a plus b plus c, and here b minus c and c minus b, which is important to know. So I'll end the video here and we'll continue solving problems together. Thank you.